Okay, in this session, what I want to do is talk a little bit about the ordinary least squares tool in ArcGIS. This is an extension of the idea of ordinary least squares, and what we're talking about here is a simple form of regression analysis. So this is the Wikipedia page in which we're talking about ordinary least squares. This is a nice, simple scatter plot with a line, best fit line running through the data. And so the idea here is what we want to do is we want to figure out how variable A is connected to variable B, and we typically do that with a scatter plot. There are lots of times when what we're doing is trying to explore whether variable A is connected to variable B. So if we looked at the Gapminder world, this is a way in which you can explore connections between variables for different countries in the world. So this is a nice project that Google incorporated as their Google Public Data Explorer, really powerful way to work through data sets. And what this is this is just a simple scatter plot, technically a bubble plot, of income per person plotted against life expectancy. And you can see that this axis has had a log transformation. If we looked at this as a linear transformation, it would look something like that, with all of the countries kind of bunched up here at the end. So a log transform helps to establish this nice linear pattern between income per person and life expectancy. So the idea is that the more income that you have per person, the longer people live in any given country. But what we might be interested in doing is establishing what countries don't fit into that pattern particularly well. So we've got countries like Equatorial Guinea that are far away from that best fit line that would run through our data right here. And that's what we're going to look at today with the ordinary least squares regression tool. So what I've done is I've downloaded the cartographic boundary shape file distributed by the census. So these are going to be the individual counties. I've selected the 1 to 20 million scale version of this. And these are going to be just some nice boundaries that are going to avoid clutter. I also downloaded some data from countyhealthrankings.org. So they put together some nice spreadsheets of data about different counties, and this is a nice way to kind of have some simple real-world data that we can work with. With no further ado, let's take a look at that. So these are the county health rankings that I downloaded for 2015. These are the cartographic boundary files. If we load those boundary files into Arc, we'll see a map of the United States, and we can zoom in on that. And so these are just simple sort of county outlines. We can take a look at the attribute table. We've got some basic information here, including state and county FIPS codes, a combination of those two, and the GeoID, county name, area of land and water, and so on. So we're gonna need that GeoID later when we want to join our data back. If we take a look at the county health rankings, we've got a number of different tabs. So what we're going to look at here is ranked measure data, and there are a lot of elements in here. So we've got low birth weight, adult smoking, adult obesity, physical activity, many more. So what I want to do is explore the link between physical inactivity and adult obesity. So I'm going to take this row, and I'm going to copy it. Actually, the very first thing I want to do is copy the state and county FIPS codes over here. So we'll do copy, and then what I'm going to do is I'm just going to make a new sheet to use as kind of a scratch sheet for now. So I'm going to paste that data in here. We'll go back to the ranked data here. What I want to do is I'm going to grab physically inactive, so copy, and paste that into my blank sheet here. And I want to grab one more thing, that's percent obese. Now, it's a good idea to make sure that if you're gathering a rate in one variable, that you gather a rate in another variable. If I had done number physically inactive versus some kind of metric data set like number of people who are obese in a given county, that wouldn't work out so well. So we want to make sure that if we're using a rate on one side, we're using a rate on the other side. So we're going to paste that in here. So one of the things about the county health data is that we have this top category here that's sort of cluing us into all of the individual things that go into that metric. So adult smoking has these 4 different columns associated with it. The percent of smokers, which is what we're interested in or might be interested in, but also a 95% confidence interval, showing us kind of maybe expectations about what that might be. This is sort of just a sample, and this gives us a clue into what reasonable numbers for that might be in high and low estimates. The upshot to this is that we have a blank column up here, or blank row rather, that we want to delete. So we delete that row and we can get a nice picture of what we're doing. And now that I've added that in here, what I'm going to do is I'm just going to copy that to a new book. And so now we've got a nice new spreadsheet. We've extracted our data, and this is what we're going to use to bring into Arc here in a second. Then the very next thing that we want to do is take a quick look here at the relationship between these 2 variables. So what we're going to do now is we're going to make a scatter plot of percent physically inactive and percent obese to explore whether there is a connection. So one of the things that you want to do before you start making the scatter plot is to make sure that your explanatory or independent variable is on the left-hand side, and that your resulting variable, your dependent variable, is going to be on the right-hand side. You can switch those if you plot it another way, but this is going to make sure that things come out a little bit more normal right from the start. So in this case, what I'm going to do is I'm going to, my independent variable is physically inactive. My hypothesis is that the less physically active that you are, the more obese that you are. The more physically inactive you are, the more obese you are. So I'm looking for a direct relationship between these 2. So I'm going to highlight both of these columns, and I'm going to insert a scatter plot. So this is my plot. We don't have the labels on here directly, but we can add those in. So if we add a chart element to axes titles, we can add in percent physically inactive, and we can add in an axis title on the vertical, percent obese. And if we have these labeled, we probably don't need that title. So what we have here is a nice plot, percent physically inactive, percent obese. There is a direct relationship between those 2. What we might want to do is we could add something like a trend line in here, and see something like that. Now it turns out that our trend line is being obscured a little bit by all of the dots that we have on here, so we could bring that to the front for a little bit more resolution. So I've just removed that trend line back here, and what I want to do is I want to add it back in here. I'm going to do more trend line options. I'm going to choose linear, and what I can do is I can label this, so we'll make sure that it's a solid line, and then change this to black, and then it's going to show up a lot more clearly. We can come in and we can add things like the equation or the r-squared value, and move those to a location where we can actually see them. These numbers indicate the intercept. So somewhere over here, the relationship between x and y, your slope value there. And the r-squared value is a metric of how well or how tight the 2 variables go together. So an r-squared value of 0.50 tells you that about 50% of the variance of obesity is explained by physical inactivity. Okay, now because we're going to want to move these things over to Arc, we're going to want to make one easy change here. So the idea is we're going to get this information into a shapefile, and shapefiles don't usually like special symbols. So what I want to try to do is change this so that it's going to be a little more shapefile friendly. So we're going to use percent physically inactive, which is probably actually a little bit too long, and percent obese. If we can avoid spaces in names, if we can avoid having them too long, there's no real need to have uppercase. So we'll change this to percent inactive, percent inactive, and percent obese, and those should be good enough for a shapefile export. I'm going to save this stuff as ols.xls, so we want to make sure that we're saving this in Excel 97 2003 format. Arc is a little bit more forgiving with this format than others, so we'll hit save. And now we can bring that data in. I actually have a previous copy, so we'll get rid of that. We've got our county data set here that we've loaded in, and I'm going to add in the file that I just created, sheet 1, and we can take a look at that and see the information. Okay, so we've got the FIPS code, state, county, percent physically inactive, and percent obese. Actually, this is an old copy, so this is before I made these changes. So we're gonna start a new session here. So I'm just gonna exit out of Arc real quick. We'll start that back up again. So pause real quick as we reload those layers. Okay, so we're adding back in our OLS data, sheet 1. The reason we had to stop is because we can't load the same Excel file back into Arc. It actually keeps a cached copy that's hard to change. So sometimes exiting out of Arc is the easiest way to do that. So FIPS, state, county, percent inactive with the new nice labels, and then percent obese. So we're going to do a quick join. So we're going to join based on GeoID, and we're going to join it based on FIPS code. So this is the state 2-digit code plus the county 3-digit code is the GeoID. That's the same thing as the county health rankings is calling the FIPS code. So hit OK. Joins tend to happen pretty quickly. So this will be done in just a second, and we can take a look at our attribute table to make sure that that came in just the way we want it. So now we have percent inactive and percent obese here. So what I'm going to do quick is I'm going to, when you do a join, that join is not actually attached to the database. So while it looks like all of this, those new fields have been attached to this data, it's really only our map document that's keeping this link alive. So a good thing to do after you've done a join, if you think you're going to not need to play around with these points anymore, is to export these things back out as a shapefile. So I'm going to export this as obesity.shape, and we'll add that back into our map as a layer. This attribute table looks like the one that we just saw, but now these are permanently attached, and you notice that the end of these got trimmed off because of the limit in how long a name can be in a shapefile. So now we can exit out of these and we can proceed. We can take a quick look at our data under symbology. We can visualize the pattern in obesity. So we see a lot going on, especially in the south, kind of radiating out from there. We can, by the same token, look at percent inactive and see something that looks like this, an even probably stronger pattern than the last one. And what we want to, so what we've got here is sort of a spatial pattern that looks coincident, and we want to illustrate that using the ordinary least squares tool. So we're going to use, we're going to do a quick search for ordinary least squares. So here's the tool. We're going to need an input feature class, which is obesity. We're going to need a unique ID field, which needs to be an integer field with a different value for every feature. We don't actually have this, so we're going to need to make it. And I'll show you how to do that in just a second. We can use a dependent variable. We can set our dependent and independent variables, but we're going to need to, since this is a required field, we're going to need to fix this first. So let's take a look at how we're going to do that. If we look at, we could quickly Google ArcGIS string to integer field. This is what we need to do. This is the first article that showed up on that list. And we've got a quick explanation, which is that we need to add a number field to the table, which we could take a look at. And then we need to use the field calculator to copy the values to the new field and convert those values to a number. So let's take a quick look at that. Okay, so we're going to need to open a table, type a name, set it to number, set the width and decimal places to certain values here. And then we're going to use a field calculator to do the values. And we can express the changeover like this, dot as number, and we're going to be using the field calculator to do that. So let's proceed with that. It's a minor annoyance, but these kinds of things come up a lot when you're working with Arc. Let's see if we can do a quick add field. So we could actually do this straight here. So we can do table options, add field. This is going to be a new ID field. A short integer would only go up to 255. We want to use a long integer. And we can set the precision to some value that's going to be higher than whatever we need. What I'm going to do is use the geoid. I could also use the FIPS code to generate this ID field. So I'm just going to set the precision to 10 for now. So now we have an ID field and we just need to calculate those values. So if we go back here, we can select the number field. We can select calculate from the field menu. So we can use something like this. And we're going to follow these instructions. So what it says is double click on the string field from the fields list. So we're going to use the geoid field. And we're going to set the type to string. And we've got a number of different functions in here. What we want to use is one second. Just to be safe, since this is irreversible outside of an edit session, what I'm going to do is cancel out of this real quick. We're going to start an editing session. So we'll need our editing toolbar. And we're going to start editing. All right, so now once we're in an editing session, we can open the attribute table. We can come back over here and we can do the field calculator. And now basically this is reversible. If we mess something up, we can always change it. So going back to string, we're going to pick geoid, and we're going to see if we can figure this out. So what they're looking for is an expression called as number. We can try this as written. That does not look like it's up here in the functions, but we can see if it'll work. So that's exactly as it's written. We can try that out. That was my guess that wasn't going to work. We can try this again. So geoid as number. Sometimes you need to do things like that. Okay. But more often, what we're going to need to do is something like this. We'll try using just that and this. And that seems to work. So just to recap what we did there to do the integer conversion, we did a field calculator. Instead of using, like they recommend, options within string, we're going to use the integer function, which is going to what's called cast whatever the input things are into an integer. So in this case, this was our outer, just to show you how this was built. This was our outer, and our inner is geoid. So we're using the function int to change things that are in geoid into a number. So this number should match this number, which it does. So everything looks good. We can go back to our editing session, save our edits, and exit the editing session. And now what we've done is we've created a numeric field so that when we want to use ordinary least squares, we have something for this unique ID field. So our input feature class is obesity, our ID field is ID, our dependent variable. So this is the out variable. This is the thing that's getting changed. So in this case, we're predicting that inactivity is causing obesity. So obesity is our dependent variable, and inactivity is going to be our explanatory variable, one of our independent variables. The nice thing about ordinary least squares is you can have more than one explanatory variable, which can be very helpful. We can also specify a report file that might be extremely useful in terms of diagnostically telling us how well that regression worked. So we're going to save this as OLS report. We'll just hit OK. So it's going to run that regression, and we'll be back when that's done. Okay, the results have come in. So this is our regression of inactivity against obesity, and let's just take a look at that. Let's take a look at the description of ordinary least squares to describe what's happening. What we're saying here, and actually we'll come back here. What we're saying here is we've got a number of different data points. We're plotting variable 1 against variable 2. We have, it forms a cloud. We're making a best fit line, but we're saying sometimes our point is above that line, has a greater value than we would expect. Sometimes it's below the line and has a lower value than we would expect. So in this case, what we're saying when we looked at our graph was, yeah, we know that there's a relationship between physically inactive and percent obese. We know that the more inactive you are, the more obese you are, and that makes sense. But what we're saying is that for certain counties, given their physical inactivity level, they might be more obese or less obese than we would expect. So we're looking at sort of the variation around here, exploring what are called the residuals, these unexplained bits of the relationship. If this were a perfect relationship, this would all be a single line, but it's not. It's sort of a cloud that goes along that line. So we're looking at which states have a higher percentage of obesity than we would expect, given their physical activity, which states have a lower level of obesity than we would expect, given their physical activity. So here's the output of that. So we're saying which states have more obesity than we would expect, given their level of physical activity, and that's going to be in the blue. Which states have the blue states would be lower obesity, given their physical activity level. Red would be higher levels of obesity given their activity level. So this is kind of an interesting pattern. So what we're seeing here is that places sort of the mid-south here has lower levels of obesity compared to their physical activity. The north has higher levels of obesity, or the northern Midwest anyway, higher levels of obesity per physical activity unit. Same thing with the west, more obesity than we would expect given their physical activity level. So this isn't saying which counties are more obese or less obese. These are saying which counties are more obese or less obese given their physical activity level, which is a very different thing. So this has been an exploration of the ordinary least squares tool. Hopefully you'll use it to explore these relationships in a little bit more detail. I should say that one way that you can kind of quickly explore these kinds of things is with using the normalization field. So we could have created a very similar map by saying obesity per unit of activity. So we're normalizing by activity. And if we had chosen a color ramp that's a little bit more similar, so let's say something that ranges from green to red, we would get something that looks like, actually let's do red to green, something that looks like this. Okay, So a fairly similar pattern, just in a different way. You can see that the colors don't match up exactly, but the general pattern holds up pretty well. And the reason for this is that we're essentially mapping the same thing. I wanted to add one more explanation of what's going on here, and that is by virtue of taking a look at the attribute table of the data that we just created. So when we ran the ordinary least squares, we took the data, our input data, percent obese, percent inactive, and we basically made a scatter plot, just like you see here, taking a look at that relationship. So this scatter plot is essentially a summary of what we see between these two columns. And remember that we had said we're measuring physical inactivity as a way of predicting obesity. So you can get both of those in here at the same time. So as you are more physically inactive, you are more obese on a county-wide level. Now, we have a prediction. So if we were at a 20% physical inactivity, we would predict something like a 25% obesity level. In this case, if we have a 22% inactivity level, we observed that we had a 24% obesity level. So our estimation would have been, given this activity level, we would have predicted that you should have been that particular county should have been 26% obese. And the truth is that it was only 24% obese. And so we overestimated by about 2.44%. So they were less obese than we would have predicted them to be. So the residual that you see here is how much you missed your mark. Negative means that you overestimated. Positive means that you underestimated. And then the standardized residuals are a z-score transformation of these, so that instead of using actual units, you're just sort of standardizing those and making them something like standard deviation measurements. So let's visualize this one more time, just using the straight residuals. So I'm going to uncheck our normalized data. And if we go in here and visualize this by residual instead, you can see that these ranges are going from negative 11 all the way up to positive 12. So this is under predicting. So this is saying this is over predicting rather. We thought you were more obese than you actually turned out to be. This is under predicting. We thought you would be less obese than you actually turned out to be. So if we apply that, the pattern looks the same. The z-scores don't actually change the numbers really all that much. They just sort of recenter them and standardize them and scale them in a way that makes them more comparable to other numbers. But maybe this makes more sense. This sort of ties things under predicting or over predicting by 11% or 12%, depending on what you're looking at. We could go in and we can change the histogram as well. So here we have 7 classes, and what we could do is we could change these to sort of simplify the story a little bit, and maybe make just 3 classes. So here I'm deleting some of my extra class boundaries, right-clicking on that line, and changing things around. And this way we can sort of we can change these values and maybe say this is maybe within a normal range of prediction, but anything greater than that or less than that we're sort of really interested in. So we could apply that. We could get a pattern that looks something like this. If we wanted to bring out that detail a little more, we could shrink these categories to really show over prediction or under prediction, something like that. If we wanted to resolve this just a little bit further, we could get rid of this middle category entirely, and really just look at whether we're over predicting or under predicting. Okay, so we get a pattern that looks like this. So this is nice, binary system. What places are more obese than we would expect given their activity levels? The West Coast, the Upper Midwest, some of the interior coast here. Which counties are less obese than we would expect? Kind of within this general framework is kind of this interior of the country that kind of the Mid-South heading into the Great Plains less obese given their levels of physical activity than we would have expected. So one more way of looking at it, and with that we'll wrap up the video. Thanks.